Okay, as promised, we want to do an example for impulse momentum calculations. And so we'll just do one example here using the impulse momentum theory. And let's say we have a baseball. So a 0.145 kilogram baseball, which I think is close to the correct mass, is thrown at, let's say, 35 meters per second towards home plate. And the batter hits it out at, let's say, hits it out into center field at, let's say 40 meters per second. We want to look at two aspects here. The first we want to look at, A, is what impulse was delivered to the ball. And we'll do it in parts for the following reason. So we want to find out what impulse was delivered to the ball. And part B is what was the average force on the ball, which opens up a whole nother discussion, but we'll see what we get there. What was the average force on the ball? So the first thing we're going to look at is what is the impulse. And so we know it's thrown at 35 meters per second, which is right there. And then the batter hits it out at 40 meters per second. Let's write the equation down first. And so the impulse momentum theory says that the force times the time is equal to the change in the object's momentum. Well, we don't know the force, and we don't know the time yet. And in fact, let's add that here. We'll say the time of impact, we'll say is equal to 0.004 seconds, about 4,000th of a second, which I also believe is not unrealistic, but we could probably do some research on that and find out. So we do know the time, but we don't know the force. So we can't calculate the impulse directly. This is the impulse here. Impulse. And this is the change in momentum. Clearly, we have to solve the right side of the equation in order to answer this question. We can't answer the left side of the equation. So we do know the mass. We do know the initial and final velocities. So let's put that in there. We know the mass is 0.145 kilograms. The velocity is 35 meters per second. So it's being thrown in at 35 meters per second. The mass is 0.145 kilograms, and the final velocity is, well, it's not 40 meters per second. The final velocity is minus 40 meters per second, because you're throwing the ball into the batter this way, and here's the guy standing there ready to hit it. And when he hits it out, it's going to be going back in the opposite direction. So since velocity is directional, we have to put a minus sign in there. Many problems don't do that. Okay, so you got to be aware that that is what you have to do. You have to make it negative. And you can see the big difference here. Ordinarily, I'd be subtracting these quantities with that minus sign there. But because it's a directional change, it's a significant impulse delivered to the ball. These quantities will now add. So let me get a calculator. And let's see what we have here. We've got 0.145 times 35. So I've got 5.075. Now we're adding here plus 40, 5.8. And the units are the same. The units are going to be kilograms times meters divided by seconds. They're the same for both of those quantities. So we're going to add those up. And we get 10.875 kilogram meters per second, which is the impulse. 875, that is. And so it could be also Newton seconds. All right, so that's part one. That's part A. Now we want to look at, we know the time it went. The time, we want to find out the average force on the ball. You can see from this equation right here, F, we know the time, we can then solve for the force, and that's the strategy behind this. And I said up here, the time was 0.004 seconds, or 4 milliseconds. So let's do part B. I now know that the impulse equals 10.875 kilogram meters per second. I know the time is now 0.004 seconds, which is 10.875 kilogram meter per second. And I'm going to divide to get the force. It's going to be 10.875 divided by 0.004. And the units are going to be kilogram meters per second, which is per second squared. This, of course, kilograms meters per second squared is a Newton. So if we divide that 0.004, we get F equals 2,718.75 newtons. And that's the average force. Now, why do I say that's the average force? Let's look at the impact of a ball on a bat. And to do that, we're basically going to say, okay, here's the bat, a very good bat, and here's the ball coming in. Bat's swinging this way, the ball's going this way. Well, when it first touches, this is force, and this is time. When it first touches, the force is going to be very, very weak. But in the next scene 2, the ball is going to start flattening out, okay, on the bat. Bat's still going this way, ball's still coming this way. Now it's flattened. Now the force has increased. Okay. Now, at some point, the ball will come to a stop, and it's going to be squashed pretty flat at one side. And it's going to stop at that point. That's going to be the point of maximum impact, okay? And then, as the bat continues to move forward, the ball is going to start to come off of the bat, and it's going to start to move away, and that force is going to be a little bit weaker. Whoops, let's get rid of that. This is still a little compressed on the bat there, and it's just starting to come off. And what we want to do is show that, and then finally, the ball will just about be touching the bat, and that's when you're down here like this. So the actual force, the actual pattern, if you will, is going to look more like kind of like a bell curve like that. Not a very well drawn curve, but that's approximately it. When we calculate the average force up here, we're basically saying that the impulse is force times time. Well, force times time, as you see in the graph here, force times time is really the area under the curve. So this is really an integral. The impulse is really the area under the force curve. That's the impulse. You can integrate it if you're into calculus. So the integral of f dt would give you that. And so that's the impulse. When we calculate the impulse, when we use it this way, when we calculate 2,718, all we're calculating really is the same area. However, over the same amount of time. However, we're presuming that this area is the impulse. This area of this in red is equal to the area in blue, but the force isn't, because you can see there's a little overlap here. And so therefore we're calculating the average force. This is the average force and not the actual force on the object. The actual force is the smooth curve that I've poorly drawn over here.